So sorry for the waiting, but the Teams was sending me into another lecture, which was really surprising. So you open a link and it sends you to another one. So this is really spooky from the perspective of data protection, but it just happened. Okay, there's a little bit of change in plans today. So the antenna, which I promised for today, will be given by an antenna expert later in the term because we made some changes. Today we're going to talk about active devices. So that's why we are here. So this is just a slight rescheduling. So there will be one or two lectures given by my colleague in late June because we thought that was a good idea. And what we will do is just make sure this is running well. Okay, this is shared and this should also be shared. What we will look at today is the things we like most because I'm doing them every day. We want to look at specific semiconductors and RF devices and things which we need in order to get good amplifiers, and also devices which are helpful. And there's a lot of learning on the semiconductor side, which is general to go ahead with the design and the devices which make our life really nice. Just to mention that the real challenge is to understand also the progress in things we are having every day. When you look at your phone and when you exchange that's I'll find that. When you look at your phone, you have actually a very good example of this progress, because maybe somebody can already say at this point what is happening in the cell phones between every generation. When you buy a new one, what is different in the RF when you do that? Just as the first idea. Is there any improvement? So when you get a new phone, which features could you relate to devices? I mean, obviously the thing has a lot of new apps, has a lot of more memory and so on. But what is the change that actually is enabled by progress in what we are discussing now? Could you say that? It's not. It's actually, in some way it's simple, in some way it's really complicated. So maybe you have some ideas. So this is a nice thought. So you're, in terms of bandwidth or accessible services, your phone expands, and there always has been. So we started with 2G. It essentially had a couple of frequencies, and today we can do anything from 2G to 5G, or maybe even beyond that. And we can do WLAN in addition. We can do all kinds of near field services. And if you would like to express that, what is getting better on the RF side? It's actually quite simple. So it's not only the expansion in frequency bands, so we go wider in the bands. So from previously up to 2.6 gigahertz or 2.7 gigahertz, now it can do up to 6 gigahertz. So there are bands which you can select. But what also must be getting better, this is something you can easily deduce. Why can we transfer always more data? Is this clear? What is the technological improvement which enables that? There's a simple idea, because when you have a phone, there's a battery, and this battery is pretty similar. So if it's getting better, you know that also from e-cars, also people working on it, but the progress in the batteries is actually it's in the percent range per capacity per volume, so to say. So that's on 10% if it's really good. So somehow the energy efficiency of what we are using is getting better, and maybe also to express that, in which way are the amplifiers getting better? Can somebody maybe try to express that? What would be an advantage for your phone if you're thinking of an iPhone 20 or whatever it's called then? What would be the real progress you would achieve? Yeah, and that's quite predictable. The efficiency of these of the devices you are using is getting better, and it's quite predictable. It's 1 or 2% per year. It's not a lot, but we have been on mobiles for more than 15 years now. And when it started, it was in the range of a couple of 10 or 20%. Now we are approaching 50, so just progressing. It's a very steady improvement, yeah. But only because of that, because it's getting more efficient, you can use it so long. Yeah? Because there's a principal idea. For every bit which we transmit, we spend energy. If this energy was constant and you're transmitting more and more bits, your battery goes flat. If the battery capacity is constant, you would have to scratch the story every, maybe if it lasts for some generation 2G for a day, maybe for 3G, it's already done at noon. Like obviously there's something in it now, so we can get some progress, and that's exactly what you're getting. So and this we need to understand, and there's a lot of learning in this which we now want to tackle. So the first idea which I want to plant in your head is that the RF devices are not scaling in the classical sense. So if you have Moore's law, which was this idea that you are putting on more and more devices per area, this doesn't fly. So you see here an RF device, and you see the feature sizes are not really small. The feature size of the gate, which you have here, is 300 nanometers. So this is, and you know, the memory has something like more than 3 nanometers by now, 5 nanometers, the most advanced memory. So there's a factor of at least 100 in between. Yeah? So, and the other thing is that also the distances, you see that here, the overall distance you can get from that reading, this is in the range of, the scale here is in the range of nanometers. So you see this is about a micron, and this is about 3 microns in size. Yeah? And if you think how many CMOS transistors, silicon could be fit on there, you would find a huge, there could be many transistors. The reason for this is quite simple, and you also see there's another structure here which is quite large also, and that's especially due to the high voltage. Yeah, so this device is more in the range of supplying 28 or 50 volts rather than what you have in your battery in the phone, which is more like 3 volts and then down. So it's a much higher voltage capability. And the other thing is that you also have maybe also a different size aspect. And then the translation is that we are using these devices also now in terms of their representation. And the representation is actually relatively simple. There are some things which you are really surprised about, which is that you get some behavior which are quite clear. So for a FET, maybe capacitances. This is something which you have here. You have an input capacitance and you have an output capacitance, which is just what you measure when you just look at the behavioral idea of the transistor. Yeah? And how did we get that? We would measure those S parameters of those devices and find out that the impedances we are measuring are simply capacitive, and we would remodel them. Yeah? So we would just try to find out what this thing does, not what it is. Yeah? And at the same time, especially the amplifying elements, and this is what you see here, this is something we need to understand very clearly, because this we are trying to improve. So the numbers you're getting are critical. Yeah? So the advances you're getting for the efficiency or for the losses, they are defined by the numbers associated for that particular device. Yeah? So My job is, if I have a GM of maybe 500 millisiemens, I try to get a technology which has 600 millisiemens. Yeah? So just to be very plain, and it's just improvement on numbers. And we are deducing this clearly from the RF behavior. So we want something to be better. We have very clear targets. And then we translate that down to on the semiconductor level on things you might even know at this point. Yeah? So that's helpful. And this is the description which I'm trying to imply here. So when we now look at the Smith chart, of course, you can guess that you're not going to look at the Smith chart only for impedances. Yeah? So I promised you that this concept was quite useful, and it's even enhanced. It is an even enhanced concept now, because when we can look at lines and passive elements, you can of course add more diagrams in there, which help you to understand also an active device. Yeah? So first of all, there's things which you have learned already, which are quite easy to understand. So for example, the impedances for the reflection coefficients for the active device are quite easily understood. So this plot is the S parameters of a FET, the input, and these are things which are really easy to be understood. So for example, a FET is dominated by its gate and its gate capacitance. So when we go to zero frequency, we are getting an open. Yeah, so what I'm just telling you is that a MOSFET has no input current, which is something you know in a way. And at the same time, the capacitive behavior is very clear. So you're seeing that what do an ideal capacitance would be going this way. Yeah, so this would be on the line. And you're seeing to reasonable frequencies, it's just the capacitance. And then you see the input impedance turning in. So that means there's an additional loss mechanism. There's just at higher frequencies, not just only a capacitance. This is something you can easily understand. Yeah? And the second thing, which is then when we go back here, so this is easily reflected. So this is apparently just a capacitor, but there are either additional elements which you need to model that, or a combination with feedback which forces the impedance at higher frequencies inwards. Yeah? The next thing is the output. That is also very easily understood. In an output, we have a capacitance, and in parallel to that, we have a resistor. Yeah, apart from the active part, which we will come to in a minute. But the output of the transistor is just a capacitor in parallel to a resistor. And if you translate that to this plot, that's quite easy. It's a capacitor and turns the same way, but in parallel, you also have a finite conduction even at real zero frequency. So at zero frequency, we here have a finite parallel resistance at the output, which is the output conductance. So that's something, there's an additional resistance visible, yeah, so that you see that you can actually deduce the output conductance there. It's a value of something like 400 ohms or so 250 and a bit going to infinity here. Yeah, so you're seeing it's a simple orientation, and then this thing behaves similar to a parallel RC. It's not really difficult. So that's something, and we've just find that you see also that the data also starts to look at something strange for those in the design course. I'm emphasizing so much also the EM thing with the possible resonances, and these resonances you see here, that at high frequency you see something which is not really on a single line anymore. This is the story. This is already a well-behaved thing. Sometimes in a FET, if you have a resonance, then all this simple stuff really looks odd. It starts to be really moving back and forth, and suddenly you have resonances. Yeah, so it's something which is not easy to be mitigated, and that's why we are very careful also to check, is the representation so good, or can there be something else which we don't see? Yeah? That's the passive part, and you see here we use the capacitors here and the CGD and also the GDS to model that. So and these values have been taken just from modeling these. So you resimulate this circuit with the S parameter, compare it to the data until you get decent agreement. Yeah? What you don't know about yet is that we can also now put in the active component into this story. Yeah? So we are now giving an active component a meaning. Yeah? And what we effectively do, we add another diagram in this, which is just to put everything in place. And so we're now adding a polar diagram, but it's not an impedance, it's not the reflection coefficient anymore. We just measure in a polar diagram the S21, which is the forward transmission. Normally this would be lossy, so it would be a number below 1 and would go down as frequency. It's still a number going down in its magnitude, but it starts at a radius which is now not 1 but 5. Yeah? So the ratio of wave of leaving the device by what is sent to the device is bigger than 1. That's a clear sign of amplification, and here you see this 5 is really the absolute forward transmission. Yeah? If it was a lossy line, just a lossy line, it would be 1 and then no that. Or also if you pinch this FET off, the scale of this would simply go here into the inner side, and you would just lose the gain. Yeah? Because an active transistor can also be switched off, so it doesn't have gain. Yeah? That's if you just turn the current down. Yeah? Then you would measure the S parameter again, and you would, on the same scale, you would go here, and then it would look like that. Yeah? And the forward transmission is also turning inward, which is in agreement with our thinking that the gain as a function of frequency effectively goes down. Yeah? But the problem is with gain that there's also a second contribution to gain, which is the feedback. Yeah? And how do we find out about that? That anything which we send forward, also if the idea is you excite something, so you have a small change, and then you have a big change here, but then what happens is that on this side of the transistor at the output, you suddenly realize, oh my God, there's something heavy happening, so there must be some feedback. And this is exactly what is modeled here. And how would I know this about now? That's very simple. How much feedback do we expect at 0 frequency? Exactly. And so we now put another polar diagram, which is starting here. So it's not in the impedance. It's an overlay diagram that you get the full characteristics in the same diagram. So this is a multiple plot. Yeah. So and we're starting this feedback here. Yeah. And then we are expanding in frequency again. So in this case it's nearly 0. So 250 megahertz to 50 gigahertz in this case. So this is 0 and this is 50. Here it's 0, 50, 0, 50. And this is here 0 and 50 for the forward. And now coming back to the feedback, at 0 frequency, nothing happens. A capacitor at 0 frequency is just an open. Yeah? So nothing happens, but the higher you get in frequency, you see that the feedback is expanding. It's going away from the 0 in magnitude and also has a phase change. Yeah? And you see the radius for this is not the same here. So for this diagram, this is a bit, you need a bit of oversight to see that. This is given on a scale of 5. And because the feedback is optimized to be low, this plot is given on a scale of 0.2. So it's a relatively small number. Yeah? The idea is that you put it into this diagram to see something. So to see the change, if we would put it on the same scale, there would be like such a small pigtail here on the side. That's why we don't do that. So in this case, we just expand the radius a bit. So this, if you look at this graph here, this is on a small expanded scale by making the scale smaller. Yeah? And the idea is now that we extract certain elements from there. So for example, we have now these 5 elements or 6 elements which we have already in the simple plot. Yeah? And then how do people progress in this modeling? Yeah? So you have some assumption what a FET looks like. And for example, if we took this diagram then we could not get, for example, this behavior here. The capacitance would simply stay outside, but this is idiotic, because if the model doesn't reflect what's going on, what you do then is you simply add a component which introduces some losses. Yeah, and for example, what we then would be doing, we would put a resistor here in addition, and then adjust it that this modeling, and especially here at the input path, that we are getting this behavior done. This is how people come to the idea, what do I need to do to model this? Yeah, so this is one idea. So we are adding, but not just because we are so smart and intelligent that we know everything. It's just trying to get it done. Yeah? And then the other thing is this idea that we have connection structures. So the FET is not just the intrinsic device, but we also account a couple of additional passive components to the equivalent circuit. Yeah? So for example, here we then add a gate resistor in the modeling, and a drain resistor and a source resistor. These are these, yeah. So they're just given there. They can also be extracted from test structures. And then we also have a little bit capacitance on the pads, which are just the lines coming in, and also inductors, yeah. And these are modeled here. And if you get the right parasitic environment plus the right values from a couple of measurements, you see that the model actually agrees with on the right reference level with what we are doing. So that's how you would approach that. Now in the RF now there's a lot of devices which are available, and what the first learning is for RF, that for reasons that the technology, like in the CMOS and the memory, there we have essentially one technology. So we are in memory and in digital we have one, maybe with different nodes, but it's essentially CMOS, and then we are going down in size. Yeah? But CMOS is also an RF device, here you have that, but it's not the only one. And the reason is that despite of all the advantages for digital, this does simply not fly for the needs we have. You cannot put 20 volts on a normal memory device. Yeah? If you do that, boom, doesn't work. So there's for example a derivation from RF CMOS, which is the LDMOS, which is the most successful device which is used for base stations then, because there we need the power to transmit to you. Yeah? Or the CMOS is also not in the transceiver parts of your recent cell phones. This is for efficiency. Yeah? And there we are just taking a bipolar device. This is why we can get your cell phones to battery lifetimes which are exceeding a day. If we used CMOS in the present situation, we would never get there. There's a technological advantage of some other device concepts over those which are presently existing in silicon. And a last statement, which is also maybe helpful for you, there's also some things where for example, one thing we clearly have as a problem is to have, for higher frequencies, we cannot generate power at all. It's very difficult. Yeah, we have real trouble especially for these new bands, for 5G, when we are going to 26 gigahertz, to have power at all, or efficient power especially, that you can put that on a cell phone. Yeah, because there's no devices which produce enough power, and if they are not very efficient. So you're draining your battery with that special feature. Yeah. So if you think of your next generation, we simply don't have the devices yet to go to the high frequencies. There's simply nothing we can use. Yeah? And then let's talk a little bit about what we need from the crystal size or from the solid state size. So the first thing is, what is a crystal? Well, what fuss do we make out of that? Yeah? And the first thing is, of course, what are we using as crystals? And that's very obvious. Why are we using silicon in the first place? It's an easy answer which you can deduce.
It's very easy to find, and it's semiconductor material.
Yeah, it's a semiconductor, but it's one which is available. Yeah? And there's a lot of this raw product on this planet. It's sand. It's silicon dioxide, it's quartz, and by this is sand. So as long as we have sand is also a rare material in the building industry, but for the semiconductor at least there's sufficient. Yeah? So don't underestimate the availability of sand, but for the numbers we need in electronic side we have enough. So that's one thing. And then, but we need to learn a little bit about why we do this. And one clear advantage of the silicon is that, and that should not be underestimated, that there is by now a technology that we can make pizza wafer, as we say. So the first idea is, why do we buy our electronics at MediaMarkt or at Amazon in a cheap way? You first of all have to get all this performance down in price. Yeah, so anything which you are doing or buying, although for you a computer is still a valuable thing, but given what the performance is in there, there is a drastic price reduction we always require. Yeah, so there's never, typically if you get a new of something, a computer, a cell phone, it's always better, same price, which means that per function you're getting cheaper. Yeah? Because it's very clear, if you have, for example, my cell phone has 64 gigabyte, the next one probably will have a factor of 4, the price of the cell phone, however, will be the same. So somehow it's getting cheaper. And why is that possible? Because this is given here. This is such a silicon rod, which can be done in 12 inches. Yeah? So you first of all can make a crystal which is essentially is of this size. And silicon at the moment is the only material, not only in the raw material, but really also in the availability of 12-inch wafers, maybe even more. Yeah? Some of the other devices which we looked at are only done in smaller quantities. It's a bit strange, but the typical other materials are done in 8-inch wafers or less. Yeah? And this is depicted here. So this is an 8-inch wafer for the which we have for some of the RF technologies available, but they're not done in quantities. Yeah. So the typical for the RF devices, typical size is still inch, while memory and all the other things are done at 300 millimeters plus. Yeah. And the question is now, how do we approach that, and what can we learn from that from the RF? I'm not going to repeat all the solid state physics, but there's a couple of items which we really need to understand, and that's important. Yeah? The first thing is that what is a crystal? A crystal is an ordered arrangement of solids or of atoms. Yeah? And you can do then a lot of things with the atoms. And the first question, my first question is, if you have an ideal crystal, what is the resistance of that? Does everybody get that? An ideal crystal has a resistance of 0. We have to talk about the conditions, but it's correct. Yeah? So when you have an ideal crystal, and you make the calculation typically first for 0 Kelvin. Yeah, so we have an ideal crystal steady. Then you can calculate that the carriers which then are arranged in the crystal essentially ideal, and because it's ideal, there's simply no reason why they should be scattered. That's a very fundamental idea. Yeah? And the other thing which without going into this very complicated calculation, there's one number which pops out which we will need all the time. Yeah? The carriers which are in there are described by the Fermi statistics, and that is a statistical argument. Something we will look at in a minute, but just for information, not for learning. And what pops out is the excitation energy of that statistic, which is the Boltzmann constant times the temperature. And that in itself sets an energy scale, which is the relevant number for these carriers, which will define everything we do. Yeah? And maybe somebody, what is the temperature we are at here is 300 Kelvin. Does somebody know the number for the Boltzmann constant times temperature in energy? We typically speak in electron volts. You know this number. What is that? Is that 1 electron volt, or is it less?
maybe it's 1.6 electron.
But that's the band gap. But when we adjust the temperature, so this number is 26 milli electron volts. So when we are exciting, the carriers will have, as a typical representative energy in this crystal, will have this number. Now you're coming. It's correct what you're saying. Now you're coming with the idea that we differentiate materials, and you then one number which is clearly important based on this theory is the band gap. Yeah? And just as a short reminder, what is the difference between a metal, a semiconductor, and an isolator? A metal, first of all, is a material which does not have a band gap. So any energy which is available can be used to get a carrier to a state where it can conduct. So there's no gap in a metal, and that agrees with our principal finding of the solids that metals always conduct. This is something we know, and this is depicted here. If you look at this from an energy, this is position and this is energy. So if you have to move a carrier, with any energy you have in a metal, you will be able to do that. That's why it's conducting. Yeah? In a semiconductor, and that comes now there's an idea when you are calculating these crystals, you get a structure, and this structure it's based essentially on the real positioning of the atoms, which is essentially a very simple idea. How do you match energy-wise best some balls, or in the case of silicon, with the electron configuration in a way that it's minimized in energy? That's what we are doing there. You can calculate that, and this minimum energy, which is then found, we get in crystals. So if you X-ray a crystal, a piece of sand, you're seeing that this, for example, in this case silicon, you have a specific configuration, and this is only because the energy of the crystal is minimized when it's condensing, and then you get numbers for the distances of these crystals. Yeah, and if these numbers exist, a direct consequence, if you then plot that on the energy level, what is happening there is defined by that structure. So that's why some materials, simply because of the configuration, are insulators. Yeah? And if we now try to put that on an energy scale, in a metal we don't have any band gap, so the gap is zero. An insulator we typically consider also number-wise in the range of something like 4 eV. This is a typical limit. When we say beyond 4 eV, we say this is an insulator. And you see that here, that from the statistics, there's the statistics just say there's a filling state for the crystal in energy. So the maximum energy all these 10 to the 23 electrons in the crystal can have, it fills up to a certain energy level. And here you can clearly see this is the maximum water level, and to conduct you have to jump here. Yeah? In an ideal crystal, and then you realize in the yellow case, this typically will not work. Now, why do I know this? Why can this not work? This is now something which is really easily understood based on what we just said. If my statistical jump energy is 26 milli-electron volt, but you see here the Fermi level is in the middle of something which is 4 eV wide, I'm jumping, but I have to go to the ceiling. So my level where I could conduct as an insulator is on the top level. So I'm looking up, and there's not, statistically nothing will work. This is the statistical argument why there's no conduction in an insulator. Yeah? And now in the semiconductor, we are now able to provide information, or also influence the properties, that we can go both ways. Yeah? So you have a certain energy gap, and this is constant. You can define that by the material choice. For example, in silicon, it's 1.12 eV. And first of all, when it's pure, you are in a situation where nothing happens, because you have essentially an insulator with a smaller band gap. Yeah? Now coming to what I said earlier, why at room temperature do we still, why do we see a resistance in a semiconductor? Because I said if it's an ideal crystal, there would be no resistance. But what is happening at room temperature with the crystal? So what is happening with everything we do when we here made out of solid? What is happening with the atoms? Yeah.
Vibration.
Yeah, vibrating. If you want to say this scientifically, it's a phonon. Yeah, so the thing is moving. Yeah, and if you ever go to Europa Park, there's a very nice illustration of that. There's something where you are the electron, so you go through something and you are swinging balls. Yeah, and the trick is you go through a certain distance and you're not being knocked out by the balls. And this is exactly the idea which we have for the phonons. Yeah. So the idea is that the temperature will swing the crystals, and if you're taken by a field or by a diffusion process in a direction, you get a bang on your head, and then you draw it again, you get a bang on your head, so you're slowing down. So that's why you have a finite resistance at any finite temperature. Yeah? So this is why this is the phonon scattering, and there will be another one which we add. The trick is now that with this material selection, and that's why we do semiconductors so effectively, we can both make layers which are very close to the metal, so we can play with the band gap, and we do that. Yeah, so we make the band gap smaller. We don't necessarily make it zero, but we make it smaller, yeah, which will favor current. Yeah. We can have other layers where we can increase the band gap by the material's choice, which goes more to insulator. Yeah, so you are sitting there and scratching your head, say, what do I need at this part of the device? More insulating, and then you can play with that. Yeah? And the other idea is that with the onset of impurities, this is the second thing, you can also change the available number of carriers. Because the message for any semiconductor is you want transport. So you want something to move, and for the transport you need a motorway. Yeah? And it's very clear to you that a very smart motorway, which is very nice, is good. Yeah? The only trick in this transport is that you also need cars or carriers on the motorway, and the traffic is how good the road is times the number of cars you can put on. And if you can increase that, you get overall a good transport. Yeah, so we need both. We just always need a good path, but you also need carriers. Yeah? And this is the problem when you just go to an ideal crystal. How many carriers do you have at zero temperature in a crystal? You have a nearly ideal path, but there's a slight problem. So you have the ideal motorways, but how many cars do you have at zero temperature in this statistics? The answer is quite simple, 0. Because there are no carriers activated. Yeah? So this is what we start. So we have an ideal motorway, but no cars. So traffic is 0. It's not very efficient. So this concept is helpful for the understanding, but at real temperatures and real carrier situations, we are different. Yeah? So maybe this helps you. And now, can I see a crystal? And the answer is definitely yes. Today we can see crystals, and we look at them every day. So this is a transmission electron microscope image of a FET. So you see the scale. This is 200 nanometers. And when we make the resolution, which we are trying to optimize now, then you actually if you see that, you're seeing the atoms. So this coarse behavior, especially here in this region, these are single atoms which you can effectively see. Yeah, so it's because the resolution of those electrons hitting, they have a very small wavelength, so they can actually visualize atoms. Yeah, and you see also this is a metal gate, which is also composed of atoms, and you see the structure of the atoms. I think from the top you can even see it better than I can. There's real structures because there's different compositions of the alloyed metal in this case, and you can really single out the atoms which you have. Yeah? So this is possible. Yeah? We can, of course, not see them optically. We can only see the electron image and then falsify them and make them visible. That's something we will also have to explain. Yeah? Now, which elements are we talking about? This is maybe also from a material point of view interesting. So what is the main material today in your cell phone when you go digital? Which materials are most prominent? Silicon, good. But the important step is what you added. Thanks for that. There's also a lot of germanium in your cell phone by now. Can maybe somebody say why that is? So why have we changed the silicon industry into silicon germanium?
Because of lower band gap.
Good. And what is the advantage of the lower band gap? Can you already phrase that at this point? We will talk about.
Lower energies to accelerate electrons.
Yeah? Yeah, it's a very smart idea. So when we want to, especially for the low power applications and making good contacts, and it's all the same argument, you simply don't want to use so much driving force, which is effectively energy, to activate the stuff. It's a very good thinking. Yeah? So you're taking a silicon and germanium, and the good news is because they're in the same period, column of the period system, you can also grow them on top of each other. So if you do it right, you can, this is important, not everything can be combined. There's few materials which you can really put on top of each other because silicon has a lattice constant, yeah. And when you do that, you have to form a crystal, and that's what it's all about. It has to be a crystal. It's not amorphous material. Anything we need in these materials needs to be crystalline and a solid. Yeah, so that means an arrangement, because remember where we started. That only works because the atoms are perfectly ordered. If they are sputtered or if they are just amorphously moved, then all these concepts of conduction break. They don't work. There will be much less in their conductivity. Yeah? It's only, that's why I start this way. Yeah? Now we can, and silicon also cannot be grown directly on germanium, but compositions of silicon and germanium can be tuned to be grown on top of each other. That's something we will look at, yeah? And that's very favorable. Yeah? The other elements we are looking at is which are helpful, is the group 3 and the group 5, and the group 2 and the group 6 elements. Yeah? So for example, let's talk about where we use them. Let's talk with the 2,6, which are also semiconductors. Cadmium telluride. Where is this used? Although it sounds a bit unhealthy, but where do we use cadmium telluride a lot, especially in the beginning? The early solar cells were very good for that. Yeah, so there was, the trick is, this is a very nice optical material. It's been also used for sensors. So this is also a semiconductor. We discarded that because the group 2 elements are all not very healthy. We are avoiding mercurium, we are avoiding cadmium because they're extremely poisonous. Yeah, so you don't want to discard them in the environment when you are discarding them from the application. Yeah? How about silicon? Is this tricky? We eat a lot of silicon, by the way, because many of our processed foods are silicon coated. It's a lot of the apples and whatever we get have a small silicon coating on top just to make them look nicer. Yeah, so it's sand, so it's completely okay, and it's they're really, by now you can eat silicon, so there's no problem with this material. Same as carbon, this is completely, at least to here, Germanium is also completely okay. So this is also a big advantage. Yeah? The 3,5s, they are not as lethal as cadmium, but they're also difficult. So boron, aluminum, and gallium, they are okay, and indium. What is a bit tricky are those guys here. So we are using the group 5 elements, which we like. And nitrogen is apparently not so critical. That's what we breathe. But there's a bit of a problem with phosphorus and arsenic, which is not so, phosphorus in our bones, of course, but especially when you have arsenic and antimonite, that's not so so healthy. So that's why we have to be a bit careful about those. Yeah? However, I'm talking about those because they unfortunately have all those nice features. Yeah? So for example, one of the most widely used semiconductors by now because of the LEDs is the white LED, which we are all using, is aluminum, gallium, and nitride. Yeah, that's the baseline of the white LED. It's a blue band cap, which is then by some conversion transformed into white light. Yeah? So that's what we're using, and it's quite okay. From a transport point of view, we are very much interested also in this domain because similar to the germanium, we like the gallium and the arsenic, which enables the cell phones. So although it's arsenic, you have them all in your pocket because they're so efficient. And also the indium is also useful. And we are just also, by the way, looking at these things because with the gallium, indium, aluminum, arsenic, and phosphide system, we can do all the colors of the rainbow, except from blue. Yeah? So we can, all the LEDs we are looking at are made from these elements. For the power, when we now think of more generation of RF power, we can do all kinds of plotting. So for example, there's simply an advantage in using materials in comparison to silicon. So silicon is good, and silicon germanium is also good, but if you plot that in a simplistic way as a function of frequency, we simply see that by some factors we get more power out of certain materials. Yeah, so that's the story. Yeah? So we simply don't get relatively the same, for the same frequency, we simply don't get the power. It's more a statistical argument. And the reason is now, what would be important exactly to do that? Yeah? And one way of looking at this is, of course, you start with what we have. Yeah? And then there's the famous founder of Intel, Gordon Moore, who, when I was born, at some point said that deducing from 4 transistors, he said he was predicting a line towards the number of transistors we use today, which is billions. And he was said that for every so and so much time, he would number the number of transistors per area. Yeah, that's the famous Moore's law. Gordon Moore, he died this year, early this year. So that was, and that's why it's called Moore's law. He's just this doubling has been going on forever. And here this is the same thing, the number of transistors on the left. Here is a very large time scale, and you see that this is essentially a straight line, even to something you still know. So the I7 is something you still might have, or derivatives of this has been on, yeah. So, and this is something which scaled from 0 or 4 transistors to presently about 2 times 10 to the 9 transistors. This is what the different transistors have. Yeah. So this is why all this digital development goes on. What is important is that, as you correctly said, and I'm very thankful for that, that today we are modifying silicon already to get the performance. So Moore's law is not just a story of silicon, it's really a story of combinations of adding new materials. Yeah, so when you see here a typical memory transistor, there's silicon, and you see that there's pockets and implants of silicon germanium in there. And do you know how these influences go? What does, so this is a crystal, But what does the silicon germanium do with the rest of the crystal? Does somebody understand that, or what are we seeing here? It's an interesting story. So we apparently was just what we see. So this is a source, this is a gate, and this is a drain. Yeah, you see the electrons are somehow flowing here, but somehow they're put in these pockets, and this is not so clear why does it look this way? Does anybody have an idea how we improve silicon? It's silicon in the middle, obviously, but what do we do with it? And the idea is we stress it, we strain it, as we say. So you can modify a crystal with a different crystal somehow included, so that the silicon, which has certain conduction properties, actually gets better when you put it under strain. Yeah? So you have a material which you always had, so it's the same silicon which you had back in 1971. But the idea is that by pushing strain on it in the crystal, in this production process, the channel which is here underneath the metal is actually improving. Just by putting, and this is why it's another, there's also, the silicon germanium is also useful to make some very low loss contacts. That was your argument, I think you said that is very correct. Yeah. So that where this activation energy is helpful, because when we are controlling a channel here in such a switch, the first idea is, of course, to have an efficient switch, not to have losses on the simple contacts. And making these contacts is already a high art where thousands of engineers work for. Yeah? So it's not something where you go, because it's always, everything is getting better a lot because of Moore's law, essentially. Yeah? And then there's another change which we didn't talk about yet. What is sand? It's not silicon. Sand is?
Silicon oxide.
Yeah. And this is probably the most important material apart from the silicon. And you can see the idea of silicon dioxide here. We have the same. This metal is aluminum, and it forms an oxide. And what is the main point about the aluminum when we use it in everyday's life? It automatically creates an oxide. And what about this oxide? When you have aluminum, you are happy. Why are you happy about aluminum, for example, in comparison to iron?
Rusting.
Yeah, it's rusting, but it's a stable rust. Yeah, so you know very well that if you have some aluminum surface, everywhere we have those, you're sitting on some, yeah, and the rust is stable. While in the case of iron, you know that your car at some point will just be brittle. Yeah, you just have, if you keep it, iron will unprotected as a rust will simply fall apart. Aluminum doesn't. Yeah? Another way where you can see also this difference is with the copper, which we also like very much for the conduction, the metals. Yeah. But you know, if you put a copper roof in any building on this planet, what is a copper roof after 10 minutes or after one rainstorm? It turns greenish. Every parliament has a copper roof. I think it's true for nearly all the nations in this room, and it's just green. Yeah? And this is the same problem. Like iron, copper is also not creating a stable oxide. Why am I telling you this? The story about this sand is that when we look at the silicon surface and we put it to air, we get the same. This oxide is stable. Yeah, so you put a silicon wafer, you have it very clean, and the surface is, without doing any much, you get already nearly a transistor. You get a silicon and the silicon dioxide. So this combination is the critical thing. Yeah? It's not only the silicon. And because of this special property, because of this combination silicon to silicon dioxide, we have this industry. It's an interface property which we are talking. It's not a material property alone. is the same idea which we have for the aluminum forming a stable oxide. Yeah? A self-sustained oxide which does not require any modifications and will not fall apart. Yeah? And that is the interesting thing about electronics. You're not talking only about the bulks, but also about the interfaces. Yeah? Okay. There's something which we need to talk about now, which makes what we are doing here different from what you know maybe from the silicon world. And you see, for example, when we are looking at RF structures, it's quite interesting when you plot them. So you cut any chip of your cell phone, yeah, so anything which has RF in it, and you see the transistors, the silicon transistors are nearly invisible. So they're they are the small items in these red box. However, when we are doing something which we are known which we need for RF, and you remember the passive thing, there we had this idea that the RF structures have to meet the wavelength in some way. So there are orders of magnitude in between. So all the connections and the things we need for the RF doing are way too big for the silicon chips. So you make a lot of transistors, and then on top you have one inductor. So there's a mismatch because as you know, the silicon transistors are on the nanometer scale or tenth of nanometers versus a silicon structure on top, which is the passive one, where we need millimeters for the wavelength. So this is a bit crazy. So that's a mismatch. So that's why it's also not very simple to use a digital memory process one-to-one as an RF structure, because you have these transistors are very nice, they're fast, but you don't have the passives. Yeah? So you need to, first of all, get out of this multi-layer stack to go to something where you can place something which is useful for RF. It's quite interesting. Now we have to talk a little bit about the materials again. So what I just showed you, there's one thing which we need to really clearly understand, that to get these excessively good properties, you need very good crystals. Yeah? So you cannot get away from this idea of having a very error-free crystal, because then what we want to do with it doesn't work anymore. Yeah? And for example, now if you take two materials, for example, as you said, silicon on germanium, or you take some combination of the gallium arsenide and some other material, then you have to first see that any material has a lattice constant. And the lattice constant is something distinct. Yeah, so there's very few materials who have similar lattice constants. Yeah? That's number one. And the other thing is also the form of the crystal, because as you saw in the one picture, the atoms can be formed in very different crystal types. Yeah? And you have to be of the same crystal type to be able to grow something on top of each other. That's a very strong limitation. So we cannot simply combine any atom into anything into a crystal. There's only few combinations which nature has given us which we can work with. Yeah? So that's very important. And now how does it work with the combination of silicon and germanium? Yeah, silicon and germanium, you can have two bad cases, or one good, one bad. The bad case, if you just grow germanium directly on silicon, it would relax, because if the layer of the silicon germanium is getting too thick, then it will take its own lattice constant. Yeah? And it's like packing billiard balls or pool balls of a different size on top of each other. And you know that if you're building that and you have different ball sizes, then you have different constants due to that. It simply doesn't fit. And then if you, at some point, the top layer will create its own structure and will condensate in the way it wants to condensate. Yeah? And then the interface will tear. And that will be very bad, because then you have two crystals on top of each other. It's impacted, and it doesn't work anymore. So and what we saw here is very important, that this is fully crystalline. Yeah? And how does it work? How can this strain also be taken over? This is something which we can do, but we can only do it for thin layers. Yeah, so and that is what we call pseudomorphic growth, that if you have the silicon on the low side, you grow something on top with a few layers only, which takes then still the properties of silicon. So the germanium is strained because it still assumes the crystal structure of the lower setting, so to say. Yeah? And this is a fully crystalline structure. And this is the material engineering we all need, and we are critically dependent on that. So this epi growth is the epitaxial growth, or this combination of growing something on top is the prerequisite for what we are doing with all our electronics. Yeah? Because if and it's just there's a critical thickness of some layers. So for example, 10 atoms on top of each other can still be grown. If you grow 15, the top layer peels off. Yeah? So it's really atom counting. That's what we talk about. And this is really the idea how we can manage such materials. Yeah? So this is important, this crystalline idea. We want perfect crystals. And because, why is that? Because we want the associated transport properties with it. That's why we do all this fuss. Yeah? Then one way of looking at this is also from the direction of colors. And this is quite attractive. What does color mean in terms of semiconductors? How do I change the color with which a semiconductor emits? What do I change? So why is something radiating in yellow, and why in green, and why in red? How do you do that? I mean, you're looking at every day in your smart screens, or maybe just now. What are the pixels? How do you make the color of the pixels if it's not organic? Any ideas?
When an electron demonstrates based on one it releases some energy.
Yeah, that's correct. But how do you make the selection?
Wavelength of the light emitted.
And how do you influence the wavelengths of the light emitted? Or the frequency at which this emits? What is it related to?
Band gap.
The band gap, yes. And how do you influence the band gap of something? If you make the choice, how do you? No doping. Doping is not changing just by a small margin. But the real point is this is the material selection. Yeah. So for example, if I take indium phosphide, I get a band gap of 1.9. If I take gallium arsenide, I get a band gap of 1.4. And if I take indium arsenide, I'm getting 0.33, sorry. And the reason I mention that is that you have to know silicon. Where is silicon emitting in the spectrum? If you go optical, which color is silicon? This 1.1.
Infrared.
It's infrared, so we can't see it. And this is why we need these materials with the higher band gap beyond silicon to have colors which we can see. Yeah, so for example, the yellow is, I will show this, the yellow is about 1.9 eV, this we can see, and greenish is going in direction of 2 something, and the red ones are, as you say, between 1 and 1.4. So the gallium arsenide with 1.4 is still in the reddish, but it's visible. Yeah? So this is a selection. So all this engineering which we do comes from the selection of layers. So an LED which you grow is simply forming the layer where the process of the recombination is done. This is in a layer which has the right band gap for the color. Yeah? Same for the lasers, for example. They have the same principles. You add a cavity that you can form a laser. So the same idea. Yeah? Now, what is critical for us when we focus? Now we have chosen materials with a certain band gap, and in color we understand it quite perfectly. Yeah. For the now what is the critical idea for the conduction of carriers? That is what we want to learn about. Yeah. And the first thing is to, with some grain of thought, to assume something like Ohm's law. Yeah. You make an experiment which is somehow wrong, but you take it for the moment. So you just check if I excite a carrier in a crystal with an E field. Yeah, that's E is the equivalent of the voltage in the Ohm's law. Then you are exciting a drift velocity of the carriers moving statistically. Yeah? And how fast they will move is defined by a material or a parameter which we call mobility. Mobility not as fancy traffic concept, as a physical constant. Yeah? Mobility. So you're checking how much speed I get when I'm accelerating with a field. Yeah? The other way of looking at this is to define the mobility with this Europa Park experiment. So I'm the carrier, and now the question is, I'm excited by my field. I'm going to the door, and the question is, how often do I get a bang? Yeah, so from the sides, the crystal I'm moving in, how often does that happen? Or how positively, how long will I survive? You know that you can define a material quality by the lifetime of carriers in the material. The longer it is, the better the crystal. Yeah? So how often do I get a bang? If I don't get a bang to the door, I'm very happy, which doesn't happen. And the second parameter is, which is very useful, is the equivalent of speed. Let me take it this way: how fat am I? So how am I reacting to the movement? Yeah? And by this, in this crystal concept, we are defining an effective mass. Yeah, so my excitation towards a field, and this is a material parameter in the transport. Yeah? My colleague Oliver Ambach always said it's whatever the mobility is, it's the Priel factor. So you have a smooth screen, this is the motorway, and the better the mobility, the smoother the motorway I'm on. Yeah? Which is influenced positively by the crystalline quality. This is this idea of lifetime. So if I get a bang, or if this crystal is not disturbed, if it's very pure, the lifetime is good. So I'm moving faster. And it's also clear that if I'm not really a strong effective mass, then it's getting easier. Yeah? The important point is that why RF is different is this plot. When you're looking at the materials now, you see silicon and germanium. So you see already why we influence germanium into silicon, because it is much lower. It's a lower band gap, so we lose voltage in these parts, but we win this mobility. You see, germanium is better than silicon. Yeah? Silicon is not bad, but it's not perfect. Yeah? Now there's other materials which have a very low effective mass or a good lifetime if in good quality, which are better. So in this case, higher is better. And it's just so the more to the top right, you are better. Yeah? And then there are different betters because there's also the band gap. And in which way is the band gap also helpful for electronics? So we so far only talked about conduction. But why do we bother about this second dimension at all? It was color for the LED, but what is the advantage of having a certain amount of band gap also available? Why band gap?
So we can control like where the current flow,
Yeah, also it's also good. But remember, to the very beginning, here. How do I improve isolation? Huh? So a better isolator is gotten if I'm having a larger bandwidth. And what does isolator mean? Which quantity can I put higher if I have a good isolation? No, that's the only control. Control will come second, but there's something you're missing before that. Control is good, but we need to state it. There's something when you're speaking about insulation. When do we use insulators? To protect ourselves from, no, not current, but voltage. Voltage. Very important. Why? No, this is a critical answer now. Why? Because we have now apparently a trade-off between the ability to conduct carriers, which is current, but what you're effectively seeing here, there's some trade-off. Yeah, this is the baseline on this in this universe, which we currently have available, about the trade-off between current and voltage. So you see that there are some privileged materials, and there is a trade-off. There's simply no, in this universe, there's no material which has a mobility of 33,000 and a band gap of 6 or 7. This is fundamental nature. Yeah? And now we have to get a little bit of idea why band gap favors voltage. What can go wrong if you have a very small band gaps in terms of voltage? Maybe just as an idea. Remember, there was these statistical 10 to the 23 electron sitting. So I'm not alone here as an electron. There's 10 to the power 23 around me. We're all jumping. And the trick is when you have a small band gap relatively with a given energy, and if you have many, it's a statistical distribution. If you have a small band gap, it's a bit strange in this room, but if I look up, we are 10 to the 23 down here. And if we have statistical and have some excitation, there's a statistical probability that some of us will reach the roof, although it's an insulator. Yeah. Why? What is the point? The point is when we want high voltage, we want essentially the band gap to be higher. So it's essentially the rooftop of this building getting from, let's say, this height, factor of 6 higher. So the probability that somebody reaches there is getting down. Yeah? So you see that. So you could play this argument and say, I don't know whether I have it. You could say this is voltage, and this is current. This is current. Yeah? So this is also an answer why we, for example, when you think, for example, in power electronics, which is a parallel lecture, we have very much difficulties in making a 20 kilovolt switch at the moment. There's simply no single switch at the moment which can support 20 kilovolts, although we would like that. Yeah? This is essentially, you could play with the system, the aluminum nitride, maybe you can do that, but you also know very clearly that if you can support such a high voltage, what this crystal can support in current will be low. Yeah? And that's why when we're thinking of now RF again, we have to sit back and what is our principal idea? What is the product of the two? Power and voltage. Sorry, current and voltage. I messed it up. Current and voltage is power. Yeah? And you see the principal power limitation is there. So you cannot get a product of the two, which is on the top right at the moment. Still, you get an advancement, and it's an exponential advancement here. There are apparently materials which are better than the system of silicon and germanium, but there are things which are simply better. Let's come a little bit. There's also some other things we have to think about. Now, I'm only speaking about materials now. This is a bit unrealistic because I'm making some assumptions, yeah? And the reason why silicon is still a major contender also in RF, it's simply there. Yeah? So even if it's bad, or not the best, you can make it on pizza wafers and relatively cheap. Yeah? So wherever you don't need the final use for, you do that. And what is just to remind ourselves very clearly why the silicon is so good, you have these huge substrates, and there's some learning in this. First of all, why do we make the substrate so wide? Just recall that. There's a very strong idea behind that. Why do we like to process big wafers instead of small ones?
Because the process is getting cheaper if we use like millions instead of thousands of devices in one process.
Yeah, very good. But the idea of pizza is actually getting quite far. It sounds like a bit trivial, but we have the building of semiconductors has to do a lot of with pizza building. Yeah? So the idea is that when you have a small wafer, you have to do all these processes, and if you have a big wafer, you also have these processes. Now, you ask the question, how many people can eat from the pizza? And the principal assumption, which is not quite true, but it's an assumption that the processing you do costs the same as if you're doing a small wafer or a big one. It's too simplified, it's not true, because the bigger machine will also be more expensive. But there's some truth in it. Yeah? So if you are comparing a big pizza and a small one, you have significant investment in making the small pizza. Yeah? There's also some other considerations that a small wafer has a lot of edges. Yeah? So the bigger you get, the more content you have. So you have less frame, because if you've ever done that, if you're cutting a 2-inch wafer, you're simply losing. It's all edge, little center. Yeah? While the ratio of the area by the surrounding gets better, the bigger the wafer is. That's very favorable also. Yeah? That's a geometric argument. Yeah? So, and the good news is now with the silicon being available and with these nice material properties, you can also make these wafers. And this is now a projection. It's very old. It's a prediction from, you see where it was started, from 2005. And what it supplies is on the very long ranges, how many square kilometers of electronics we are producing on this planet with which generation. Yeah? There's no solar in there or solar cells, it's just electronics. So you see you're starting in the early times, you had something like square meters or square, maybe hundreds of square meters. But now when we are looking at here where we are producing hundreds of square kilometers of electronics per year. Square kilometers of memory chips. And it's an excessive behavior. There's also one mistake in the prediction which they made. We started with small wafers, so silicon at the time was also done in small wafers, but now has increased to pizza, and they predicted also 450 millimeters. This is the effect I said. At some points they realized making another step, so going to half a meter to the super pizza wasn't efficient. So they stopped the development. There's people work still on that, but this comes much later. Yeah, so 450 millimeters, there's not a single fab yet which can do that, because it's simply too large. Yeah, but you see the development, it will come, and we are mostly at the moment at 8-inch and 12-inch where we are fabricating our electronics. And the trick is now when you make these wafers, and that's even done still in Germany, there's Wacker who are making actually these rods, so you can go there and look at that. So this is what you eventually get when, so you have a slice of this Döner there as a chip in your cell phone. Yeah? So this is they're making big rods, and the idea is that you can do this with this precision in a very perfect crystalline environment. How is it done? So how do you get from this silicon dioxide to the pure silicon? You reduce it. Yeah, that's one trick. The next one is this is a gas typically, then you clean it first chemically. So you have gas cleaning to come to very clean precursors, which then make up the crystal at some point. And then you have a crystal which is condensated, and then you're starting with this floating zone thing. This is what you see here. You're essentially heating a crystal, and by diffusion you drive out all the dirty stuff in the crystal. So anything which is still in there is, by inductive heating, is taken down, and it's actually coming here to this end. Yeah. So, and the reason why this happens is it's a concentration gradient. You heat, and because there's a gravitational aspect in that, but there's also a diffusion aspect because you drive with a temperature distribution which is taken around that. You take the unclean part out, and you also heal the crystal so that you effectively get an atomically clean surface. Yeah? But this is only in the crystal. Then the next thing is, of course, to dice it, so to saw it, and then the reason why silicon works so well is that you have a very nice first mechanical lapping, then mechanical polish, and then chemical polish, so that in the end you have a pizza which has an atomic surface. That is why we can do this stuff which you do in the cell phones. Yeah? So it's this making these wafers, yeah? And the silicon at the moment is the only material where we can take it to these sizes. Yeah? For example, for the others, because of the material properties, there are simply no substrates to make that. And here it's the same for gallium arsenide, for example, which is also a contender in your cell phone, but there you have it up to 4 or 6 inches. It's taken out of the molten, so it's a growth method also. So there's a crystal in a bath of gallium arsenic at very high temperature. You see here 1500 Kelvin, so it's hot, has to be reduced from all incursions of other materials, and then it's taken out and kept as at a growth border. So the crystal, so there's a molten material, and then you draw it out, and then it crystallizes exactly at this interface. And if you control that very homogeneously, you also get a very nice crystal. Yeah? Same as then you do the same sewing and polishing and chemical polishing, so you also get flat wafers, but they're only 6 inch. I showed you 8 inch, but that never really happened so far, so it's 6 inch still in the gallium arsenide. Yeah? There's also one learning from this. For example, we always think that optoelectronics is much more prominent than electronics, but all the LEDs, which we do on gallium arsenide or indium phosphide, they are still done on 3 and 4 inch wafers. Yeah, so all these little pieces we see glowing everywhere, they're not done on large wafers as we typically think. They're done also on such small wafers, which is a bit surprising always to me. Okay, and then the next step is, which is then once you have a crisp, when you have the pizza, so you have the basic dark, so the substrate, so to say. For the pizza, it would be the dark. And then you just, the next step is to put the active device on top with the same materials. Yeah, so you grow silicon on silicon, or you put silicon germanium on silicon. But that is a different process step now. So it's really, you get the substrates, and then essentially it's putting the tomato. Yeah, so and it's really an independent step, which is also done by a very different method. And the reason is that in this case now you can start mixing materials. Yeah, so when you make crystals, you have one type of material, But when you then do this epitaxial process, you can then include silicon germanium, or you add a silicon layer and you can do sequences of the active layers. That's the idea. Yeah? This process is hopefully fast because you have to grow it, but it's still very good. Yeah, so it's still keeping the crystalline structure very nice. Yeah? You see here some examples for the growth temperature that's in the range of 500 degrees. And the reason why that is that we, just to take a little bit of advancement for next week, this is for gallium arsenide. So how do you do that? It's essentially you put a gas stream with a precursor. So there's a lot of organic carriers, and what you do is you create, it's like an airplane flying and dropping something, not a bomb in this case, but it's like a gallium and arsenide in this case. And if you mix the gas proposition right, at the right temperature, there's always one gallium, one arsenic, one gallium, one arsenic. And we do it at high temperature. Why? Very simple, because then the movement of the carrier on the surface is still arranging to a very perfect crystal. Yeah? So if they're landing, but then they may have not gone to the right position, but because of the temperature, they're still moving. Yeah? And you have a relatively significant material incursion. You're growing atom by atom, but if you put enough gas and do this with the right way, then it's a very steady growth. Yeah? What is also important is that this is a perfectly laminar flow of the gas, so there's no turbulence at all in this. So this thing is running at 500 to 1000 degrees, but you have an absolute laminar flow of the surface. So this is the trick. And then you remove all these organic airplanes, so to say, and you keep the material. Yeah? And then you have a more or less perfect crystal. And this is it's called CVD, chemical vapor deposition, because you just put gases in the right conditions and you get the crystal. And the precursors are metal organic, and they are remove that. The trick is, you could ask why what is so critical about it, and I'll just show you what it is. It's essentially a relatively simple reactor which has this laminar flow and a gas cabinet around that which provides all the gases in the right order. So it's essentially a gas cabinet with a bit of reaction. Yeah? And the reason is that these gases which you provide are perfectly unstable. They're also not very healthy, so it's arsenic and all that. But it's also these molecules are not stable. So you first have to get them in this flying condition that they are exactly doing the right dropping. So it's pressure and insertion speed and all these things that you're getting right, and that it really forms then a perfect crystal. And this when we are visiting ERF at the end, you can see that. So you see it's essentially a room. So MOCVD is from here to the door, and the actual reactor speed is something like, it's such a pot, yeah? And it's relatively normal conditions. So it's a few millibars of pressure in nitrogen and hydrogen, and then these added precursors. That's how you do it. Right? And why is this important? Just coming back to here, you're by now making square kilometers of electronics, plus the solar cells, which have a similar thing, plus the all the LEDs we are producing by now with the same method. Yeah? So you're getting very atomically grown layers, but already on the area size, you are quite huge. So like approaching Baden-Württemberg as an area, but in memory. So that's maybe something where you're starting to think. Okay, I want to stop here so you get some idea what might be important. And next time we're going to talk a little bit about properties which are extremely relevant for us. So and I hope it's interesting, because when you talk about energy efficiency, this is how you make things energy efficient. Yeah? So this is what defines energy efficiency. This is really how can we make it and how can we make it better. So that's the final idea. Thank you very much.